Hey everyone, welcome to The Explainer. Today, we're stepping into what honestly feels like a high-stakes cyber thriller, but it's actually modern physics. We're looking at a wildly fascinating June 2026 paper by Jaime Moreno and an international team of physicists. And look, this isn't just about some abstract chalkboard math. We are talking about a fundamental vulnerability in the absolute bedrock of our emerging technological future. So let's just dive right into this, because what these researchers discovered is essentially the ultimate quantum heist. Quantum entanglement. Now, I know you guys already know the mechanics of entanglement, but in the context of Moreno's research, this is the central resource underpinning all emerging quantum technologies. Think of it as the impenetrable vault for our future data. But here's the catch. To actually trust that vault, we rely entirely on accurate verification. If we can't perfectly verify that entanglement is actually happening, well, we simply don't have a secure system. Section 1. A dangerous assumption. At the very heart of modern quantum physics, there's this massive conflict. On one hand, you've got this pristine theory that relies entirely on the assumption that quantum measurements can be realized exactly, perfectly, without a single scratch. But then you have the reality of being in a lab. The paper points out that as the complexity of a quantum system grows, this assumption becomes incredibly unrealistic. So we're basically left with this widening mismatch between the perfect theoretical models on paper and the messy, real-world experimental implementations. So this leads to a pretty critical question. Can this widening mismatch actually be exploited? If our theoretical models are expecting perfect measurements, but our experimental reality is always going to be slightly imperfect, does that create a blind spot? I mean, imagine our impenetrable quantum vault has a security camera that just glitches for 1,000th of a second every single hour. Can a sophisticated attacker exploit that tiny fraction of a second? Section 2. The entanglement illusion. Moreno and his team essentially built an adversarial attack to exploit this exact blind spot. Here's how they did it. Step 1, they leveraged that very assumption of exact measurements. Step 2, they adversarially encode arbitrarily small measurement errors directly into the apparatus. It's literally a Trojan horse hiding inside the testing equipment. And the result in Step 3? They successfully tricked the system into falsely certifying high-dimensional entanglement in completely separable systems. The tests where they saw an entangled state where absolutely none existed. And the craziest part? This wasn't just some theoretical thought experiment. They actually proved it in the lab. Astonishingly, they used classical photonic states, encoding the illusion using the spatial degree of freedom of the photons. Think about that for a second. They didn't even use quantum states to fake the quantum states. And most importantly, they deployed this trick against well-established entanglement verification tests. The exact security systems we currently trust to tell us if our quantum tech is working were entirely fooled by classical light being manipulated in a very specific, adversarial way. Section 3. The 0.23% hack. 61. In the quantum computing world, as we all know, dimensional complexity is everything. The team didn't just fake some simple entanglement. They falsely certified entanglement spanning up to 61 dimensions. That is a highly complex quantum state. To trick a system into thinking it's observing a 61-dimensional entangled state is a massive feat of deception. It absolutely proves that this vulnerability scales to the exact kind of high-dimensional systems we're relying on for future technologies. And this is all it took, 0.23%. That is the measurement fidelity error they introduced. This minuscule, practically imperceptible deviation in the measurement was all it took to completely break the verification test for a 61-dimensional system. We're talking about less than 0.25% of error. Just think about the terrifying leverage of this hack. You've got this massive, incredibly complex target, a 61-dimensional quantum system, and it is completely compromised by a 0.23% measurement fidelity error. It demonstrates just how profoundly vulnerable our complex quantum devices are to incredibly small adversarial perturbations. The attacker doesn't need to blow up the vault door. They literally just need to whisper into the ear of the security guard. Section 4. Securing the quantum future. I want to use the author's direct words here because they really carry some weight. Quote, "Our results uncover a fundamental vulnerability in current methods for high-dimensional entanglement detection. A fundamental vulnerability. Look, this isn't a small patch we need to download. It means the very way we currently test for these high-dimensional states has a massive blind spot hardwired right into its foundational assumptions." So to fix this and actually secure our tech, the research demands a major shift in how we do things. First, we have got to discard the assumption of exact measurements. perfect, pristine theory just does not exist in the lab. Second, we have to acknowledge our susceptibility to these small adversarial perturbations. If a 0.23% error can fake a 61-dimensional state, we are incredibly susceptible. And finally, the big takeaway. We need to develop secure verification methods for quantum information that are actually robust to bounded discrepancies between theory and experiment. The security protocols of the future have to mathematically account for the reality of unavoidable experimental errors. Which really brings us to a critical crossroads in modern physics. We are racing toward a future built entirely on quantum entanglement, and we're trusting it to be the ultimate secure foundation for our data and communications. But if our most advanced quantum tests can be fooled by a fraction of a percent of error using nothing more than classical light, how secure is the future of quantum information really? It's a huge question that physicists and engineers are going to have to answer before the quantum revolution can truly kick off. Thanks so much for joining me on this explainer. Definitely keep asking those questions, and I'll catch you on the next one.